So shall we start or you require some break?
No, sir.
Okay, so we'll start.
Yes.
Now Mr. Raghuram has explained you how the physical model works. It's my duty to explain you how the numerical model works now. So I will try to make it very briefly and just introduce you the key concepts what we are going to use over the 5 days and why they are necessary. So in this lecture, we will be learning some basic principle of hydraulics and open channels because all our models and everything we will be doing for the rest for our 5 days is based on the open channels and basic hydraulics what we will be knowing. Just I want to refresh your thinking. The things you have learned that basically. Then Sen-Vinand equation that professor also Datta sir also explained that it's a Sen-Vinand equation. Basically, it is derived from the Navier-Stokes equations, and it's a simplified form of the Navier-Stokes equation for the numerical model 1D or 2D. So we'll seeing it for basically for the 1D. So how the unsteady flows and everything works using a Sen-Vinand equations. I will not go into the derivation. I will just give the equation and explain you the physical meaning of each terms rather than deriving. You should know what are the physical meaning of these terms and how they are applied in your Hecras or any other numerical model because it's a simpler form. It can be applied to any equation. So how the partial derivatives and solves and the things can be learned. How the Hecras do the one-dimensional modeling. Basically, we will be learning all the three concepts. Basically, conservation of mass, energy, and momentum, and how to apply this over the various problems. Then framework and the standard step method, how it is implemented in the Hecras, and then the practical applications where we'll be using this model in the river engineering works. So just it's a brief introduction kind of thing. First part we will be starting with the hydraulics and open channel flow. So three important characteristics of the water we should know is that it's incompressible. Means you cannot compress the water. So it has to change its depth or velocity to make it flow. So you cannot compress. Air can be compressed, but water cannot be compressed. So either it should change its shape. So it can increase its depth, or while moving, it can increase its velocity. So that is a very important property. Low viscosity. So water can accelerate easily. There is a least resistance. The viscosity is less. So while flowing freely, it has no problem. When we try to retard that water, when some barrages happens or some structure is there and it retards, it cannot retard smoothly because it has very low shear strength. So this very thing is important, that incompressible, which means it changes depth or velocity, low viscosity, so it can move freely, and it has no shear strength. So while retarding, it changes to forms, standing waves forms. So if you see the flow is moving from the supercritical region to the subcritical region, it cannot retard smoothly. So hydraulic jumps form. So that properties comes into your play because of the shear strength. Now when we see open channel, we are saying it's open to the surface and it is the atmospheric flow. It is driving. So atmospheric gravity is driving this force. So the geometry of this doesn't come into play. If it is a pipe flow, then it's a pressurized flow and the equation changes. So here we are dealing in the Hecras or 1D numerical modeling for the open channel flow, where the geometry is exposed. The top surface is exposed to the atmosphere and everything is governed by the gravity. So this is, we are dealing with the open channel flow. And when the water flows in the open channel, it gains the velocity because of the kinetic energies. It is flowing from the high grade to the low grade. While flowing, it gains the velocity, and this gain is opposed by the friction. So the river has the frictions when it is moving through high regions. So it gets the frictions. Shear stress, what we have discussed. This causes it to retard. So when this both forces are balanced, when the accelerating force is balanced by the retarding force, when then we can say the flow is in the uniform flow because both are exactly matching. But in the nature, it's very difficult to match this both condition, that is forces causing the flow and retarding the flow. So in the, if you consider the all the equations what we learn are basically derived for the uniform flow, that the Bernoulli's equation or other things what we are saying, there are assumptions when we see the hydraulics books or open channel books that this flow is prismatic and it is a uniform flow. So this condition we are generally ignoring, we are not reading, but these equations are developed based on this uniform flow and prismatic channel flow. So whether these are applicable or some factors we have to introduce on a numerical model to adapt to this condition. So the simplified forms we can use for the hand calculations, but we are going in the numerical model, we don't have to deal with the hand calculations, we can increase with the complexity, then the partial derivatives and everything come into the play, but solving the equation manually, that become difficult. That's why we have made the simplified form of these equations. So when you say the uniform flow, the depth is constant along the channel, velocity is also constant, and what you say the when these two are constant, the slope and roughness has to be constant. Then only it can flow. So all these factors are constant, and it's very rare in the natural rivers. You cannot achieve this condition in the long channels. In the suppose in Narmada main canal, it is very long canal and the flow properties are remaining the same. Then we can say it is a prismatic channel. But if you say in the Brahmaputra river, it's not a uniform flow. The non-uniform flow is a thing we get in the nature, and basically here we are dealing with the gradually varied flow in the Hecras. Hecras cannot model very rapidly varying flow. So if you are dealing with the hydraulic jumps or some energy dissipator kind of thing, this is not a tool to be used. It can model some to extent because we are using the momentum equation, but it is not basically meant for. The Hecras is meant for the gradually varied flow. So this is the prismatic channel where we see that the depth is constant. So slope is parallel to the water surface and water surface is parallel to the energy grade line. This is the general assumptions we make while deriving the simplified equations. So as explained that uniform flow occurs when the gravitational forces are exactly in balance with the resistant forces. This is very difficult to achieve in the nature. In generally we are dealing with the non-uniform flow, that is a varied flow condition. Over the distance the flow changes its characteristics. So in the natural rivers we cannot assume the prismatic channel because there is no constant section, it changes from section to section. So at 100 meters or 50 meters the section changes of the river, it's not going to be a constant roughness. When you consider the bank portion and overbank portion, the n value changes. For the overbank portion, we have to consider very high n values because there is a lot of resistance. There may be some trees or some settlements may be there. Because of there, a lot of resistance is there to the flow. So we have to consider different n rather from the channel. The constant slope is not there. It's always varying. So obstructions are there. So in a river, we see a lot of obstruction in the kind of bridges or weirs or some structures we are considering like spurs, embankments, that are also creating obstructions in the river channels. And then second type is a flow condition, because this is very important, because as Raghuram sir explained you, there are the various regimes in which regime you are modeling your flow. In the upstream region, if you consider the velocities are very high, and because of the high velocity, the Froude number generally increases. And when the Froude number is above the threshold, it is greater than 1, we say it is a supercritical flow. And in supercritical flow, the boundary conditions are different from the subcritical flow. In the supercritical regime, your boundary is controlled in the upstream region. So that is very important to note. So first we have to see what are the regime we are modeling, what are the flow velocity we are expecting. Then only we can model, because if you are having a high velocity and you are modeling as a subcritical flow, then your assumption is basically wrong and you will get the wrong results. So it's very important you identify in which zone you are doing the studies, and in some time you have to apply the mixed flow regime also. So where it is in a transition period where it is flow is changing from supercritical to subcritical and again supercritical. In this kind of region, you have to apply the mixed flow regime. So this is the flow condition we have run from the energy diagram. Also, we know the specific energy. It's only one depth is possible for the critical. Then above and below, it is a below it's supercritical, above it's a subcritical. So energy diagram, this classification is there. But from the modeling perspective, you have to remember what are the velocities and likely Froude number. The first initial calculation you do, you'll see the calculation table. You will be that madam and sir will be showing you the output table. Just go through the Froude number what you are achieving. If there are any changes, you have to rerun the scenario. So these are the flow conditions. The flow conditions we have to see and then run our model. So these are the just example how the changes over the short period of time. If you are considering a reservoir, it is a subcritical. When it comes to the weir, at certain point there is a critical depth. At depth, we try to have the rating curve because there is only one depth. So at always a measuring structure, we have to measure a critical depth because that will give only one depth. Based on it will not based on the regime. So critical depth, if you use the sanding wave flume or any other flume, it is based on the concept of the critical depth. So at a certain point, when it is passing through the weir, it will be passing through that critical depth, and that critical depth is the location you should measure because what we say in the rating curve is the CD L raised to 3 by 2. CD is constant, L is constant, length of weir is constant, the head is changing. So at what portion you should measure that hair? That is very critical. It's a critical depth. That head is a critical depth because it is not depend on the flow region. So that H is there. Then again, when it passes through the spillway, it gains the velocity because the head is changing. The kinetic energy is increased. So velocity is increased. Because of that, Froude number increases. Then you come to the sealing basin. You have the plain region. Forms as at the zero shear space, it will try to retard. So it will form the hydraulic jump. The hydraulic jump is against a mixed flow condition. It will be coming from the supercritical going to the subcritical, and that region will be transition zone. And again, it will come back to the river flow, and it will become subcritical. So in the short distance of a reservoir, if you say about 100 to 200 meter, you can witness all these flow conditions. Even in the weir also, you can witness. So you have to see where you are modeling. If you are modeling for a backwater curve, it is a subcritical condition. But if you are modeling some transition, then it's very difficult to get in the Haycrass. So you have to maybe choose some other tool, like physical modeling. And basically, physical modeling is ideally suited for this because a lot of changes are taking place, and the numerical model is not capable. Even if you go with a three-dimensional model like CFD, then also this it's very difficult to capture because what you are using the scheme for solving the equation is not stable for these sudden changes. Because the model, when you say model become unstable, means it's not getting convergence because we are using the Navier-Stokes equation. They have to converge. When they converge, we get a solution. But in the short period of time, if we are changing, there are a lot of changes. The equation, there is a shock wave and it doesn't converge. So you have to go with the physical model in that cases. So ideal cases, like if you see, the spillway is always modeled with the three-dimensional structure with the geometrically similar scale. There no distortion is allowed. But if you are going for the Brahmaputra river, distortion is necessary because that depth will be very less and the viscous force will become predominant. So you have to choose what are the scenario you have to model, and based on that, which is the tool you have to use. Either physical model, it's not about the cost or time. Sometimes it's become mandatory to use a physical model. Numerical model is not suitable. If you are doing some drawdown flushing, then that drawdown effect cannot be modeled in the numerical model. In that case also you have to go with the physical modeling. So the kind of phenomena you are modeling, that governs your the model tool, numerical or physical. So these are the same figure. It is in a represent gradually varied and rapidly variant flow. In natural channel, flow is generally gradually varied. Velocity and depth changes from section to sections. That's why we use the Haycrass or any other numerical model. And energy and mass is always conserved. So this principle is best for the numerical model. But for the rapidly varying flow, you can use the momentum equation, or some empirical equations are adopted by the Haycrass, and that can simulate the rapidly varied flow in the Haycrass model. But Haycrass model, generally speaking, it's a gradually varied flow, not for the rapidly varied flow. But some scenarios like in bridges or some junctions, when the flow changes, that is accounted by using momentum equation. It has the explicit choice whether you have to go with the energy equations or momentum equation. When you compute the bridges, that option that madam will show you which scenario you have to develop. And secondly, for the sudden changes, So that we have to see and adapt. So basically in this HEGRAS we will be using the energy and mass conservation. So shallow water equations, these are the fundamental equations on which our model depends. So Saint-Venant equation is the conservation of mass and conservation of momentum basically. Mass is the continuity equation and conservation of momentum is the dynamic equation that we use. And this is used for the complex analysis like dam break analysis where the flow is rapidly varying. So hydrograph analysis you are doing, flood routing, so tidal flows. Then it becomes unsteady flow and you have to go with the momentum equation. So continuity equation means if you just if you consider one block of uh, what you say cube. Now when the water is entering and water leaving out the cube, that scenario you consider. It is called as the control volume. That is Eulerian methods. Okay, we see the fluid at the fixed position. In Lagrange method, we travel with the fluid. So in Eulerian method, we say that the fixed part we are considering. The fluid is we are considering as a cube. So fluid can enter from one phase and leave from one phase. So it's a one-dimensional model. If you are considering all the two phases, so it becomes a three-dimensional model. So in the one-dimensional model, we are saying basically it is leaving from one phase and leaving the other phase. And what changes are taking place during that time, that we are using the continuity equation, the mass. So when the suppose it's 100 cubic discharge is entering and 50 is coming out from that system, so that some change has to take place in the control volume itself. So the depth has to be increased or decreased. As the flow is coming less, the depth will increase. That storage change that is accounted in the continuity equation. So if you consider this block and two phases, what is entering, what is leaving out, and if there is a change in coming and leaving out, some change has to take place in that cube itself. And that change in the cube is called as a storage change. So your flood depth will increase or decrease based on the parameter what is coming out. So that is the continuity equation. And this is a mathematical representation. Basically, what I have told is uh, this is the change of the cross-sectional area. Means what is the change in the storage? What is coming in and coming out difference if you take from this rate of change of discharge. Something has to change. If the discharge is coming in and out is same, no change will take in the storage area. But if the discharge changes, some change has to take place in the storage area, and that is accounted by DA by A by DA by T is the rate of change of the cross-sectional area, the change in the storage area, and change in the discharge over that period. If it's having the cube space, suppose cube is having DA by X is the length of that cube, it is traveling that distance, and that change in the discharge over that space is called as a rate of change of discharge. And now when the second is the first we have covered is the conservation of mass. Now the conservation of momentum. Basically, momentum is the force is equals to mass into acceleration. This is the Newton's second law. Now you have to consider all the forces what are going to come in your system and what are the accelerations which are causing that forces. So forces are basically what are the forces which are creating the flow. That is the gravity you are using for creating the flow, and second flow is a resisting force. So these are the forces. And acceleration, how the water moves from one part to the another part, that is a acceleration part. So there are two types of acceleration, local acceleration and convective acceleration. So local acceleration, when you say it's a how it changes. So velocity changes from 5 meter to 3 meters. Suppose we are saying from one section it is having a velocity of 5 meter, and the next section it is having a velocity of 3. So we can say average 5 by 3, 8 divided by 2 is a 4. But how that velocity changing in that space, that gradient is there. How the velocity changing over that space, that is the convective part. So local part and the convective part, we are both considering this part. So how the velocity changes. So if you solve this equation, what we get is a rho delta q by delta t, that is local acceleration term, how the discharge is changing over the time at that phase. Second, this is the convective acceleration, how the flow is changing over the distance. When it is moving from 5 meter to 3 meter, we know that it's changed, but how it is changing? What is the gradient at every part that dabba x distance it's traveling? How it is changing? That gradient we get from the local acceleration, and that is very important term. We don't want to get just the velocity how it's moving, how it is changing. The changing part of the velocity is given by the convective acceleration. These two accelerations are there, and this is the pressure flow because we are moving in the open channel. There is a pressure flow, so the pressure difference is there as we move. So this term is accounted by the head basically, and the friction. And what is the gravity? One is having the local acceleration. This is the gravity and is opposed by the friction. So what is the force we are creating and what is the opposition? The net, that will be the resultant force that will be applicable. So the forces are these gravitational forces and resistive forces and the pressure force, and these are the local acceleration. So when you consider F equals to ma, the force equals to mass into action, these terms balance out, and then we get the momentum equation. So when we use the momentum equation in the numerical model, when you are modeling hydraulic jumps, hydraulics of bridges, drop structures are there, control drops are there. In the reverse we are using it for to change the gradient. Steam junctions, in HECRAS you will be learning these bridges and steam junctions. Other things, hydraulic jumps and drops are not possible in HECRAS. Since the transition is strong, external energy loss due to friction are assumed to be zero. So energy loss we are considering it as zero because it is happening in a very short distance. For the long distance, suppose in kilometers, then energy becomes predominant. Now the conservation of the energy. First we have seen the conservation of mass, that is the continuity equation, conservation of momentum, and now the conservation of energy. So basically we are dealing, if you are dealing with the open channel forces, then we have the three energies basically. Potential energy, that is because of the height. At one height there fluid is there, then it's moving to the lower height. So potential energy difference is there. Then the velocity is moving, the kinetic energy is there as it is moving. And third, the pressure. It is static pressures are acting on the both faces. That difference is help in carrying the water. So the three forces are there. Potential energy, kinetic energy and pressure energy. And the sum of this total energy gives a total energy. And you have to conserve this energy. So the Bernoulli's equation comes into place. Bernoulli's equation is regarding the conservation of energy. It is derived from the first law of thermodynamics and applied to the energy equation. So how the balancing of these terms take place has been established by the Bernoulli's, and this is very famous Bernoulli's equation. What we get, V square by 2G is the kinetic energy, then this is the pressure energy, and Z is the energy due to elevations, and these two energies are balanced and equated by the force, because there are going to be some losses, and that losses we are accounting by the head loss, because it's not a prismatic channel or anything, so head losses are going to happen, so that we have to account. Then only these two parameters can be equal, the energy can be conserved. One dimensional modeling concept, what will be seeing? First assumption is flow properties vary only in the downstream direction. So this is a basic assumption. We are considering a one-dimensional flow. We are not considering the cross flow. So it's a one-dimensional. It is changing in the downstream direction. Simplified observation, simplification, velocity and depth are averaged. We are not getting the velocity component. If you say in ADCP as a sold as told, it has the three components. But we are not going to get the three components of the velocity in the HECRAS model or one-dimensional model. We'll get a depth average velocity and depth average properties regarding that. And flow direction is parallel to the channel central line. And most of the rearranging problem we can solve using this basic problem, but not a specific condition like the spillways and other things that cannot be modeled using a 1D model. Basic concepts, standard step, that is the heart of 1D numerical modeling. Basically what we are saying is you are assuming water depth at particular section and computing the water surface at other sections as you move upstream or downstream. Suppose if the flow is a supercritical, we have to assume the depth on the upstream, and then compute downstream. Why upstream and why downstream? That are the basic questions that should come into your mind. Because when the flood is traveling, there are two things: the flood velocity and the wave velocity. In the supercritical flow, the flow velocity is very high, and the wave velocity, what is coming, it is very low. So it cannot travel upstream. The basically the flow will be pushed downward, and the wave velocity is coming. So the control is on the upstream side. So that's why you have to consider the upstream section and start your computation. Whether in the downstream subcritical flow, the velocity is low, so wave velocity can travel upstream and downstream. So in that case, you can control water at the downstream level. As the flood velocity passes, you can take your calculations from the downstream to upstream. So that is the reason why we are considering the upstream on the supercritical reaches and downstream on the subcritical reaches. Because the wave velocity, wave celerity, you call it more technically, wave celerity cannot move in the from downstream to upstream in the supercritical flow. So that's why your section is controlled on the upstream. In the downstream, it can travel in the both direction. So you can consider at the downstream part. Then the standard set method is very simple. What basically is saying, start with the known water surface. We are giving here, what we are saying is the upstream or downstream. The boundary condition is there. So we are specifying one certain depth at a particular section. The last section of the model, suppose is the subcritical flow. Now at the last section, you are specifying some depth. That is called as the boundary conditions. So you will say it is compute using a normal depth. Normal depth means Hecra software will do the calculation based on the n values. It will come up with some depth. That depth will be your known depth. For the next section, it will try to now compute the what is the water surface depth. So how it will calculate? So it doesn't know how to calculate. So it will assume certain depth. Based on that, it will calculate the cross-sectional parameters. That is cross-sectional area, hydraulic depth, velocity, conveyance. These all properties it will calculate based on the assumption. Suppose 100 meter is the downstream you have given. Next cross section it will assume 101. Do all this calculation, cross section area, weighted perimeter, everything it will calculate, and it will come up with energy. So we have to apply the friction losses. The friction losses is the distance between the cross section and is the what is the friction. The friction comes from the Manning's formula. Basically, what is the Manning's n we are considering, and that we can adopt in your friction factors and apply the energy equation. So when this matches equation E1 equals to E2 plus head losses what we have computed, then we can say the what depth you are assumed is correct. Otherwise, you have to repeat with 101.1. Now assume the 101.1, again calculate the parameters, compute the energy, compute the head loss, and compare these two things. If it matches, the solution converges. Otherwise, next iteration. So basically, Hecras what does is it does all this process automatically. So your trial and error process has been reduced by the Hecras basically. So number of it can compute thousands of iterations in 1 second. So how fast that it is. So basically, Hecras is a model developed by the Hydrologic Engineering Center. That is the U.S. Army division, U.S. Army Corps, and RAS stand for River Analysis System. HEC is the HEC Hydrologic System. It is a part of U.S. Army Corps, and RAS, HMS. This becomes a part of your model. HEC is the common. RAS is the river analysis system. HEC is the hydrological modeling system. HEC HMS, what you say is the hydrological model. They are developed by the US Corps of Engineers. And capabilities of this HECRAS is able to model the water surface for the steady flow condition, unsteady flow condition. You also can do it. Sediment transport modeling is there. So sediment transport modeling means basically if you are trying to see the regime of the flow. Suppose you have constructed a reservoir and you want to estimate how the sediment will get accumulated in the reservoir over the period of time. So that kind of analysis, if you want to do, you have to go with the sediment transport analysis. And third and fourth part is the water quality analysis. So now water quality has become very important. AI analysis we have to carry out for the most of the DPRs. So if you are concerned with the water quality, it has the specific module for the water quality analysis, and that can be used. So it has the facility to compute COD, BOD, other ecological parameters. They are incorporated in the model. So basically you are running the hydrodynamic modeling, and based on the top you can add the sediment model or ecological model like water quality analysis you can do. But basic remains the hydrodynamic modeling. Once the hydrodynamic model is done, you get the parameters required for the sediment transport. So based on that parameter, the transport capacity of the section is calculated, and whether that section will be depositing or eroding, that is decided, and then it is continuously carried out over the longer period of time. So HECRA's application in river engineering, basically it can be used for the flood inundation mapping. That is the primary purposes nowadays. For emergency action plan and everything, we need the flood inundation mapping. Flood protection design. Suppose we want to design a levee or embankment and assess its changes, how it's going to impact, what are the water levels expected after the embankment because we are restricting the channel, what are the erosions expected. That kind of analysis, if you require, you can do the flood protection design also from this dam break analysis. So HECRAS has a specified module for the dam break analysis where you can specify the dam breach parameter, and Ali sir will be explaining you how these dam breach parameters are given in the model. There are empirical based equations, physics based equations. Both equations can be incorporated in the HECRAS depending on the scenario and type of the dam and what flood you are expecting. That model can be run. Then bridge and culvert designs. These are the standard for the bridges you require. What is the waterway you are designing, whether it is sufficient, what is the afflux that will create, orientation of the bridge. All these aspects can be studied in the HECRAS model. Channel modification. Now, if you are channelizing the river, you are doing some channel modification. Whether that channel modification will be suitable in the longer period of time, whether it with the channel you are developing, whether it will get silted up. Suppose you are dredging a channel in the Brahmaputra river for navigation. If that channel is going to silted up over the period of time, then it has no value. So the channel modifications you are planning, that can be first studied in the model and then implemented. So that becomes very important. Levee design, as I have explained, and in the water quality, habitat modeling, some for specific species of the fishes, whether they can stay there, what are the oxygen contents they required, that can be studied, and water quality assessment. So basically, HECRAS uses the energy equation for all its calculations. Apart from those, for a few special cases like hydrology, where we have to go with the momentum equation. Breach hydraulics, it is a combination. You have the option in that editor whether you go with the energy or momentum equation. And VR drops. VRs, basically they are using a empirical equation. So they are incorporated in your schemes, numerical schemes. And key advantage of using HECRAS is can handles complex channel networks and structure automatically. So we can design it. So whether it is a tributary joining or whether it is a dendritic pattern near the delta, both the scenarios it can be easily modeled. In all regions we can model from the upstream with the supercritical flow to the delta region where the dendritic pattern is there. So all these capacities are built in the HECRAS model. And again it is based on the standard step method. So energy equation is used. It calculates the head loss based on the friction factor what you are giving and the length between the cross sections. Convenience calculations is doing, and computer handles all the iterations like standard step iterations. What I have tell that computations for depth, area, everything for each iteration, it is automatically handled, and I have to give the convergence distance. So generally it is 0.001 feet. I think the convergence is there. So when the solution converges at that point, it goes to the next calculation. So convergence, that parameter is a tuning parameter. You can tune that parameter in the HECRAS. But by default, that is it. And this is the implementation of the standard step method. Basically, channel bottom is there. Yeah, we are saying the head because of that elevation, the Z. Then this is the pressure heads, and these are the velocity heads. And this is compensated by the energy loss. So these two system matches. So the Manning sayings, basically Hecras is using the Manning's formula for its friction computation. So Manning's equation can relate the channel geometry, surface roughness, slope, and flow velocity and distance. So it can take all together this into account while calculating the friction. And this is basically a Manning's formula. This is, and what are the Manning's value you should use in your model as the initial guess? Because all these values are for the initial guess, not for the final. The final, as told by Raghuram sir, we have to match the values what are observed in the prototype, because it has no substitute. Because you can start, because when you want to run the numerical simulations, you have to start with some assumption, but whether that assumption is true or not, you have to find it, and that you have to check with the prototype data, that is actual site data, gauge discharge data what you are having, or some water levels during the eye floods if you have measured, whether that water levels are matching or not. Otherwise you have to fine tune your model, and fine tuning in the basically in the 1D models means you have to update your n values. So n values plays a very important roles in this 1D computations, and these are the just guidelines for initially starting the model. These are not the final values. Final values you have to calibrate it, validate and calibrate over a certain discharges and validate for certain discharges. So validation and calibration both are very important. Otherwise, numerical model has no value, to be very frank, without calibration. And these are the more detailed values in the bank portion maximum range. This is from the Vendichow's book. We have taken this value. They are given based on the site condition. You can choose and what are the maximum or minimum permissible values you should be using. That details has been given in this formula. And these are the other parts. The first part we have seen is the Manning's, that friction we can take, and there are the contraction and expansion coefficient, because the river either narrows down or expands. So that we have to take into account. And that is generally in the Hecras. If you see, there are contraction and expansion coefficients are there. They are given by the default by the Hecras. We don't have to change it normally. But for some fine tuning exercise, you have to fine tune it. So it is editable, but generally it's not recommended to change that. But certain for model calibration, you may use that. These are the values. The Hecras manual we have taken. This is contraction and expansion. Losses due to expansion are usually greater than the contraction. So when it expands, the losses are more. So expansion coefficients, what you see on the higher side. Losses from the sharp after transitions, because if it changes in a narrow portion, that are much losses than the gradual changes. So maximum values is up to the 1. And energy losses basically Manning's, then contraction expansion, and bridge and culvert you have to take its small values. The transition that are also given in the bridge editors. These values are given. And what are the data required for the numerical modeling? Basically is the channel description. What is the cross section? What is the length you want to model? And what are the channel roughnesses? What are the n values you have? Boundary conditions, depending on the type of the flow condition, supercritical, subcritical, you have to specify the boundary at the upstream or downstream. And each structure, if you are modeling some structure like bridge or weir, we require the structural details. So what is the height of the weir, what are the gates in the weirs, what are their location, this detail we require basically from the structural geometry. So I think this part will be explained in more details over the 4 days period. I just want to give the glimpse. This is the geometric editor, and here we specify all the geometric properties of the Hecras river. So in this case, the main channel is there, and one tributary is coming and joining this river. And these are the values. This cross section, how to fit this, and this is the part we are concentrating in the next 4 days. So I will not explain. Just to give the brief glance. These are the x and y values of the channel cross section, and as I mentioned here, these are the expansion and contraction coefficient. These are given by default, and this parameter, how this parameter left over bank distance and other things, it will be explained in more details in the subsequent lectures. So cross section spacing जो है, that will be explained during the lectures, because these are the part of the spacing. So RAS mapper we are dealing more specifically with how the cross section should be placed. So Generally, we have to place it at 90 degrees. So change at the distance should be sufficient that the change what we are expecting is modeled correctly. You have to don't take it too far away or take it too near. So optimum spacing is there. Some guidelines are there. That guidelines will be explaining you during the uh, RAS mapper lecture. This is all the parameters, because n values we are giving it different for the channel portion and overbank portion, and how the total computation is worked out. Manning's n for the overbank, channel, and overbank. So the three different sessions are there, and how it is integrated in the Hay class. And boundary conditions, how to specify what are the boundary conditions generally available to you is a known water surface. This is the best boundary condition we can have, because we have the known. You have gone to the site, measured the water level for that particular depth. That is the best condition. Second is the normal depth. It is computed based on the uniform flow, and you know the limitations of the uniform flow. So normal depth is the second best option. Rating curve. So if you are placing a weir or barrage, so there is a rating curve developed on the site. That rating curve can be used for the barrage or weir. And then there's a critical depth. If you are transiting a system or designing a standing wave flume, in that case the critical depth becomes a very important, because that is the standard depth. And supercritical flow, as I have explained, you have to maintain in the upstream, subcritical flow downstream, and mixed flow you can give it on both upstream and downstream. This is the second part, is the flow editor, how the flow data is given. I think this will be explained in the next lectures. Then you perform some analysis based on the geometry and the flow data what has been provided to the model. We compute the water surface process. In this, when you say compute, the standard state process what we have explained, that is taking place in the background, and the calculations are done, and we are getting the values for the or the total distance for each cross section, what are the water levels and velocities we are getting. So this is the important parameter. You can check this Froude number. What is the Froude number? If it is coming less than 1, so, and if you are giving it as a subcritical boundary condition at the downstream, it is okay. But if some transition are there, some it is changing, it is better advise you to run it in the mixed flow condition next iteration. And if the flow value, the Froude number is consistently high with a Froude number greater than 1, it is advised you to run the next simulation based on the supercritical and change your modification to the upstream side. So based on the outcome, you have to again develop a scenario whether these assumptions what we have made is correct or not. So water surface profile you have calculated here, water surface elevation. You have to check this elevation with the actual prototype data at particular cross sections. Whether it is in the 5% or 10% tolerance zone, then only you can say your model is giving the correct results. Otherwise, this model has no value. It is just guesswork. Unless it is validated and calibrated, this is just a guesswork. Best possible guesswork you can say, but not a correct representation. And you get the more detailed version. But in a cross section, if you want to see what are the various properties, the hydraulic depth and everything that is required for the sediment computation, it has given the more detail. So what is the flow area, weighted depth, and all these things. If you are placing a weir, what is the flow passing through weir, what is flow passing through the lateral weir, that distinguish also we can give from this. Limitations of the 1D model. The flow is steady with respect to the time. We are basically using a steady flow state condition. Flow is gradually varied with respect to the distance, rapidly varying its and dominant forces and in its directions, basically in the downstream direction. That's what I have to cover in this lecture. Second, Now I will explain the how you do the calculations for selecting the bed material in the model. That was one of query how to perform the calculations. So basically, what we give is a Shields method. First, I will explain. That is the data what you get from the numerical model or from the field data. That is what is the input cross section, weighted parameter, n value, and this slope. What is the slope of the river? D50. What is bed material, D50 of the bed material in the prototype, and scale, what you are assuming. Because first we have to assume one certain scale and then only we can proceed for a calculation. So proto calculations first we give it is the hydraulic depth. So we are given the formula if you see here. Basically Manning's formula you are using this all calculations. So based on this you can perform this core calculation. Most important part is that we have to compute the shear stress. Okay, the shear stress we know. Then critical shear stress we have to compute. Critical shear stress, as the if you say that spoon curve what Raghuram sir was showing, that critical value what we see is the 0.06. Above 0.06 there will be the moment. So 0.045 to 0.06, that is the range where there is a movement. So in this case we are considered 0.06. We know the specific weight of the water and sediment, and D50 what is there. We know based on this we can compute the critical shear stress. Now we have computed the shear stress, critical shear stress, the ratio we have calculated. This is the critical shear stress shear stress in proto and the critical shear stress in proto. That ratio we can compute. Up to this point is clear. Gamma RS shear stress. There is no simple formula. Gamma R from the hydraulic calculations you get S is the slope of the river. How you calculate the critical shear stress? It's the Shields formula. This formula you are using threshold as a 0.06. This computes the critical shear. We compute one ratio. That's up to this point is clear. So that ratio we have to match in the model and prototype. So the model calculation now comes into play. Then we compute the model n based on the proto n. Then velocity in the model. How we compute this velocity? Again, Manning's formula we are using. Based on the scale, we are know the actual velocity in the proto and the scale. So root n is the scale basically. So square root we have taken. Then we compute the hydraulic depth in the model. So same formula if you are seeing. Based on this gamma RS now you can compute. We know the depth, we know the area, so we can compute the gamma RS based on this hydraulic radius. So why these computations we have done above calculations? Because we have to compute the R for the model. R depends on A and P, and so we have done this calculation. Slope is constant because slope is independent. Whether you are reproducing in the model or proto, the S is going to be same. And based on this, we compute the model. Yeah. Now we know the ratio. That ratio we have to make it constant. So we have to calculate the critical shear stress in the model. So critical shear stress is 0.006 in the model. And if you substitute this in this critical shear stress, in this formula what is unknown is the D50. Because we know the critical shear stress, we know the specific weight of water and sediment, and we know the critical parameter, how it's moving. Now D50 is we have to compute. Now we calculate the D50 and that is coming 0.002. So it's very low. So we have to redesign our scale. That is the trial and error process we have to follow. Basically what we are computing is the shear stress of the model. Based on the Shields formula you calculate the critical shear stress. Take the ratio of these both. So the ratio is constant. We have to match that ratio in the model and prototype. Second, calculate the critical shear stress what will be reproducing in the model. We know the critical shear stress. We have to know, we know the ratio. So we know what is the critical shear stress required in the model. For that critical shear stress, what will be the particle moving? That we have to compute. That particle again from the Shields formula you now comes to there. So critical shear stress is known. Yeah, specific weights we know. D50 is unknown parameter what we are calculating for the model, and again the 0.06 is the threshold value where the moment will be there. So now we get the D50 for the model. So that particle we have to use. So that particle should match whether particle what you are having in the model. So that should be the computational procedure we are using. So any other question? So if you have regarding the numerical modeling or in this physical modeling, you can ask. So I will be able to try to answer your questions.
Sir, you have referred this HECRAS manual site.
Huh.
Sir, is it available online?
Yeah, it's freely available. This software and manual, this both freely available. In the afternoon session, we'll show where the website to download, and their models, user manuals are there. And now they have modified the user manuals to include the videos for a particular section, not for everything, but some portion, because the creator of that user manual always says that people like to watch rather than read. So now they are in the user manual also they have added some videos for a scenario base. So that videos are available, and the best part why HECRAS is more popular than other open source software, because they are providing you the zip file of the all the input data. So suppose you are reproducing a particular scenario, they will give the pre cross sections, post cross sections. What are the assumptions? Suppose discharge or hydrograph what we are using, they will provide that in your file. You can take that, import that in your model and run the simulations. So that easy they have made. So it is always welcome you go through the user manuals, and there is lot of help is provided in the user manual pages. And we also frequently need the user manual help, because we don't remember all the features. The main features what we are using in daily is there, but there are a lot of features for fine tuning, for sediment model. If the model goes unstable, what are the parameters to be tuned, that are best described in the user manual, and it is highly recommended that you bookmark this page for user manual. So when you start developing your own models, you will need that page frequently. Any other questions? So I think we should break now for the lunch, and after lunch we can start with the hands-on session. So from tomorrow onwards, we'll just keep one lecture, and we'll be moving to the hands-on. So rather than sitting in this room and listening to the lecture, I think we should move to the other room and do a lot of more things. Just to give the glimpse how the equations are developed and how the models are developed. This was necessary. Sorry to bore you all.
There is one announcement. Tomorrow there will be one yoga session. So all are requested to attend by 8 o'clock in the soil laboratory in here only.